Hello, welcome back. Today we will be continuing with the nozzle flow characteristics. Now, continuing with the previous, we will be undergoing or we will be understanding till now what we have done. We have studied about ideal nozzles. To be precise, ideal, isentropic nozzles. Now, so continuing with the same, we will understand regarding the real nozzles. Now, comparing with my ideal nozzle, real nozzles would be having the losses as well as some flow of internal energy is unavailable for conversion of into kinetic energy, which is our main agenda for the exhaust. So, the principal losses, which are the divergence of the flow in the nozzle exit sections, is a loss that varies as a function of the cosine, right? The function of the cosine of the divergence angle for conical nozzles, and these nozzles can be reduced with well-shaped nozzle contours. For example, let us understand this better clear. The divergence of the flow, particularly in a CD nozzle, the divergence section, if this is my so and this is my nozzle exit, the angle say alpha, right? The loss that occurs in a divergent section, particularly through the nozzle exit flow, it varies a cosine of the divergence angle, particularly for conical nozzles, and these nozzles can be reduced with a well-shaped nozzle contours. Means instead of keeping a straight edge, we can put some bell-shaped edges, right? Bell-shaped edges in order to recover those losses, right? And a small chamber or a port area cross sections relative to the throat area or the nozzle actual contraction, that is A1 to the AT, cause pressure loss in the chamber and slightly reduce the thrust as well as the exhaust velocity. The low velocities, particularly at the wall boundary layers, reduce the effective average exhaust velocity by 0.5 to 1.5%, right? And the solid particles or the liquid droplets in the gas may cause losses, perhaps up to 5%, depending on the particle size, shape, as well as the percentage of solids. The unsteady combustion or the flow oscillations may result in small losses. The chemical reactions within the nozzle flow change gas composition as well as the gas properties and gas temperatures amounting up to 0.5% of the total loss, right? Apart from considering the bell-shaped nozzles, right? Apart from considering my bell-shaped nozzles, whenever there is a combustion takes place in a combustion chamber, right, the solid particles or the liquid droplets that are in gas may cause a loss, perhaps up to 5%. These are dependent on the particle size, the shape, as well as the percentage of solid element that is being present in the exhaust gases, right? The unsteady combustion or the flow oscillations in between uninterrupted workflow may result in small losses, such as some injector might not work properly or might not function correctly over the period of time, and during that time what happens, there might be an unsteady combustion due to the improper flow or improper injection of the fuel as well as the oxidizer inside the combustion chamber, due to which what happens, there may be some fluctuations or oscillations in the flow at the exit of my nozzle, right? And chemical reactions within the nozzle flow, right? If let's say for any air or any gas which tends to oxidize or react with the nozzle wall, in a certain area to form, let's say, solid or increase the temperature, which alter the gas composition in terms of as a catalyst, or gas properties in terms of its temperatures, pressures, or its reactivity, all are also amounting to at least the 0.5% of the loss of the total thrust that is being generated. Now, the chamber pressures as well as the overall performance are lower during the transient operations, particularly during start, stop, as well as pulsing. Let us understand the chamber pressure. The combustion chamber pressures as well as the overall performance is lower when the transient operations, such as whenever you are starting a rocket engine, right, during start of a rocket engine, during stop, as well as during pulsing. Now, where do this occur? Basically, whenever you are initiating a launch, particularly you are exerting the pressure onto the earth so that you leave the earth's surface, right, during the launch session. During ascent, you are starting. At that time, what happens? You will be starting with from initial chamber pressure of 0 till your target pressure, right? And during this, what happens? The chamber pressure as well as overall performance during that particular period will be low. Similarly, during stop or descent, right? During descent or during halt, what happens during this? Basically, you will be decreasing from the operating pressure or the target pressure of the chamber to 0, right? Now, what happens during this? Basically, as the target pressure becomes 0, you will not be having anything, or the overall performance during that particular certain period of time will also be less. Now, in between, what about pulsing? You are creating random or controlled operation, right? What happens under pulsing? Let's say over a period of time, for this particular section, you want the rocket engine to be off, on, off, on, off, on, right? And during my tenure of operation, what I want a specific interval of the rocket engine to be off as well as on, right? In this case, what happens? You are intermittently starting as well as stopping your rocket engine. And during this, what happens? The chamber pressure, right? The chamber pressure as well as the overall performance will be varying, right? Will be varying. Now, continuing the same, any gradual erosion of the throat region, right? Any gradual erosion of the throat region increases the diameter perhaps by 1 to 6% during operation of uncooled nozzle materials such as fiber reinforced plastics or carbon FRPs. Now, and in this turn will reduce the chamber pressure and the thrust by about similar 1 to 6%. Now, such throat area enlargements cause a slight reduction in specific impulse, usually less than 0.7%. Now, what happens under your CD nozzle? Right? My combustion chamber, the burnt gases, right? The burnt erosive gases will be moving out or converging through the convergent section, and right after my throat, they will be diverging, creating a supersonic flow, right? That is my actual case. Now, in this case, what happens if I am putting my unit, let's say for 1 meter as my throat area, right? 1 meter as my throat area. What happens? Initially, as there is a newer start of an engine, what happens? The throat area remains same, right? after a constant time, right? After a periodic interval, what happens? As the combustion chamber or a combustion gases directly come towards your throat, if there is an improper combustion or the properties of the exhaust gases are erosive in nature or reducing in nature, what happens? They tend to erode the throat area, right? Initially, for 1 meter, it might increase anything greater than 1 meter, although it might be in the 1 to 6%, but this increase in throat area will reduce the chamber pressure, right? Which reduces the chamber pressure as well as the thrust that is being generated. Now, the non-uniform gas compositions will also reduce the performance. How? By an incomplete mixing or else incomplete combustion, right? Every time, whenever we are mixing our fuel plus oxidizer, we are planning in such a way that upon their complete combustion or mixing as well as combustion, you will be getting a clean hydrocarbon chain, particularly by under stoichiometric ratio. Right? Under stoichiometric ratio, we tend to mix, but in some cases, let's say by the failure of the pump or the failure of the injector, the proportions might vary, right? This might cause my incomplete mixing or else incomplete combustion, right? Now, due to this, what happens right after the combustion chamber, we will be having a non-uniform gas composition, which will reduce the overall performance of my rocket. Now, real gas properties may noticeably modify gas composition, that is, the actual values of K as well as mass or molar mass, which cause a small loss in performance, which is about 0.2 to 0.7%. And an operation at non-optimum altitudes reduces the thrust as well as the specific impulse for nozzles. For the fixed area ratios, there is no loss if the vehicle flies only at the altitude that is being designed for an optimum nozzle expansion, that is P2 equals to P3. And if it flies at higher or lower altitudes, then the losses, particularly during the portions of the flight, can amount up to 10% of the thrust that is being compared with altitude compensation. And these conditions may reduce an overall vehicle performance between 1 to 5%. Right? So now let us understand this a bit. What do we do? Basically, whenever we are designing a nozzle, we are designing it to operate under certain altitude, right? To have an optimum expansion ratio, particularly nozzle expansion, that is nozzle exit. Let me just is equals to nozzle ambient, right? The exit pressure of the nozzle should be equal to the exit pressure of ambient. As we know, as the height of or the altitude of my rocket increases, the atmospheric pressure decreases. So, in order to maintain this optimality, we are supposed to increase my exit pressure, right? Or in case if it's on the sea level, as my pressure is more, I am supposed to decrease my exit pressure, right? In order to maintain my pressure equality. Now, what happens under this? No. Although a rocket engine that we are creating will be able to operate under a certain regime of an altitude, right? If you are creating a rocket engine for we are creating a rocket for sea altitude. What happens? You can't discard the same rocket engine right after it's giving out after 1 kilometer, right? You will be designing a rocket engine such a way that from sea altitude or sea level to be frank, to a certain kilometer range, let's say for 10 kilometer, where during this pressure region, I will be creating my lower stage engines, right? As soon as the higher stage of engines I am being staging, at the time I will be designing a rocket engine to work from 10 km and above to optimize my overall performance of my rocket engine. Now, if I am considering only single stage engine, at the time what happens? The nozzle, right? The nozzle might not be able to compensate the same amount or to maintain the optimality during its flow time or during its flight time. So, due to this, what happens? The overall flight vehicle performance will decrease basically from 1 to 5%. Now, considering my next topic, that is my boundary layer. Understand this clearly. Now, real nozzles always develop a thin viscous boundary layer that are adjacent to the inner walls, whereas the gas velocities are much lower and in a free stream region. Right? Let us understand this bit. The boundary layer, if you are considering a pipe, right? Whenever we tend to push out a liquid through a pipe, what we can observe is basically the fluid which is towards the wall will tend to move slower rather than the fluid that is at the center of the whole cylinder or the whole tube. At the time, if I am putting my, if I am drawing my velocity curve, what happens? This will be a basic profile where the maximum velocity will be occurring at the center of my pipe and the minimal amount of velocity is at the wall of the tube or wall of the pipe. Now, understand this. Why this occurs? Basically due to a viscous force. Right? What is the viscosity? The basic thickness of the fluid that you can feel. For example, honey is more thicker as compared to water. Right? So, which is more hard to flow? Honey needs more amount of time or more amount of force to push it farther rather than water. Right? Similarly, whenever you are considering a real nozzle, right? In this case, let us change this to a nozzle, right? From your throat. What happens? As the flow tends to increase, sorry, just a second. Right? The flow immediately next to the wall, the flow velocity is absolute zero. Right? Beyond the wall, the boundary layer may be considered as being built up against the successive annular shaped thin layers of increasing velocity until the free stream value is reached. The velocity of flow region closest to the walls is always laminar as well as subsonic. But the higher velocity regions, the boundary layer, the flow becomes supersonic and can be turbulent. Right? Now, the local temperatures at some occasions in the boundary layer can noticeably be higher than of the free stream temperature because the conversion of kinetic energy into thermal energy that occurs as the velocity is locally slow and by heating the viscous effects. The flow layer immediately next to the wall will be cooler because there is a heat transfer to the wall. These gaseous boundary layers have profound effect on overall heat transfer to the nozzle as well as the chamber walls. They also affect the rocket performance, particularly in applications with very small nozzles and also with relatively long nozzles with high nozzle area ratios, where a comparatively high proportion of a total mass of 2 to 25% can be a low velocity region of the boundary layer. High gradients in pressure, particularly temperature as well as the density, and changes in the local velocity, particularly direction as well as the magnitude, also influence the boundary layers. Flow separation in nozzle always originates inside the boundary layer. Right? Let us understand this. The figure shows the flow conditions at a nozzle exit clip at high altitude, which shows the streamlining boundary layer, velocity as well as the temperature profiles. Right? Now, let us see. Now, this is my wall. nozzle valve that I have been using, and this is my nozzle tip. Now these are my streamlines. Right? What you consider this, what we have discussed basically is the velocity is slower, right? The velocity is slower nearer the wall and is increasingly away at the center of my nozzle, right? So as the velocity is slower, the flow will be under subsonic and laminar, whereas the velocity will be supersonic and turbulent at the center, right, where my flow will be higher. Now during this, what happens? The flow separation, right after the exit of the nozzle, what happens? As in the high altitude, the temperature, or sorry, the pressure of the atmospheric pressure is less. So what happens during this? The flow, which is slower, tends to expand out, right? Tends to expand out because as there is less atmospheric pressure, they tends to move out. So as being moving out, the flow tends to move till a degree of 180 degrees. Now considering the same, the velocity profile as the temperature profile, there will be less velocity at the tip, whereas the flow tends to increase, right, and remains constant, again will be decreasing at the exit of my nozzle. Now coming to temperature, as there is small shift in between the subsonic to the supersonic one, what happens? The temperature will remain increasing and will be a constant volume right after the interface region, then again constant till the area of supersonic one. Now considering the 4 performance parameters, right? Now there will be, when using or coding the values of thrust, specific impulse as well as the propellant flow and other performance parameters, one must careful to specify or as a bare minimum qualify the conditions under which the particular number applies. There are at least 4 sets of performance parameters and they are different in concept value even when referring to the same rocket propulsion. Parameters such as thrust, specific impulse, characteristic velocity and exit velocity, as well as the mass flow rate, should be accompanied by a clear definition of conditions under which they are being applied. First one is my chamber pressure, which is also for cylinder chambers, the location where the pressure prevails or is measured, particularly at the nozzle entrance. Ambient pressure as well as space of vacuum. Next, nozzle expansion area ratio, whether this is an optimum. Next, the nozzle shape as well as the exit angle through which the gases are being ejected. The propellants and their composition with the mixture ratios and an initial ambient temperature of the propellants prior to ignition or start. Now, the nozzle alignment, when the thrust vector driven for the propulsion system does not go through the center of mass of the flying vehicle, a turning moment exists that will rotate the vehicle while the thrust is being applied. A predetermined controlled turning moments may be desirable and necessary for turning or for altitude control of the vehicle, which can be accomplished by thrust vector deflections as well as the aerodynamic fins, which is being separated by altitude control or rocket engines. However, any turning becomes undesirable when the magnitude or the direction is unknown. So this happens when a fixed nozzle in a major propulsion system has its thrust axis misaligned. A large high thrust rocket booster system, even misaligned by a very small angle, that is less than a 0.5 degree, can cause a major and upsetting turning moments during the firing. If not corrected or compensated parallelly, The small misalignment can cause a flight vehicle to tumble or deviate from an intended flight path. For such turning movements not to exceed a vehicle's compensating altitude control capability, it is necessary to align very accurately the nozzle axis of each and all propulsion systems that contain fixed non-gimbal nozzle. Normally, the geometric axis of the nozzle diverging exit surface geometry is taken to the first axis. The special alignment fixtures are necessary to orient the nozzle axis with less than 0.25 degrees of the intended line through the vehicle center of gravity and to position the center of the large nozzle throat on the vehicle center line, say within 1 or 2 mm. There are other type of misalignments such as irregularities in the nozzle geometry, particularly out of the round protuberances or unsymmetrical roughness in the surface. Transient flow misalignment that occurs during the start as well as the stop. Uneven deflection of the propulsion system or vehicular structure under load. Irregularities under gas flow, particularly due to a faulty injector or uneven burning rate of a solid propellant or a liquid propellant. For a simple unguided rocket vehicles, it has been a customary to rotate, particularly spin, the vehicle to prevent any existing misalignments from being in one direction only or evening out any misalignment during the powered flight. In the cramped volume of spacecraft or a launch vehicle, it is sometimes not possible to accommodate the full length of a large area ratio nozzle within the available vehicle envelope. So the nozzles of altitude control thrusters are sometimes cut off at an angle at the vehicular surface, which allows more compact installation. This gives us a simplified partial section of a flight vehicle showing two altitude control thrusters, particularly this and this, with a scarf-filled nozzles to fit a cylindrical vehicular envelope. Right? This is my rocket body. Right? And this should be my a complete nozzle. Right? In order to maintain my aerodynamics, what we did, we basically removed this particular section of my nozzle. Right? That gives me what? Basically a cross or a half of my full length of a nozzle. Now during this what happens, the gases that are tended or that are pushed down happens what? They tend to move faster from one of the direction, which tends to give out the effective, right? The effective movement from the vehicular axis in an unwanted path. So in order to do this, what we should be doing, we should be realigning the nozzle in such a way to give out the required moment irrespective of the position. The thrust direction of the scarf-filled nozzle is no longer along the nozzle axis center line, that is this, right? As it is fully symmetrical nozzle, the nozzle exit flow will not be axially symmetric, right? These will be deviating somewhat out, right? So this is regarding our nozzle alignment for altitude control as well as the rocket engines for rocket vehicles. Now continuing the same, we will be continuing for all the regarding the pulse rocket motors and all types of rockets under next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.